Good morning, everybody. We'll start. So, what we are going to do today is conclude the chapter on linear actuators, or actuators which are not motors, linear rotors which are not motors, and we'll start with motors next week. So, last week we talked about moving coil actuators, we talked about moving magnet actuators, and we started talking about moving iron actuators in the context of snap. So just to remind you, I showed you a demo. When you take a moving iron actuator, it doesn't seem, we are not seem to be able to control it over the whole operating range. As we start increasing the current or the voltage, at some point it snaps. We don't have full range, and I told you to think a little bit about it. Why it is. So what I want to do is to go through all this a bit more formally. So first I want to derive the formulas for moving iron actuators, and then I want to derive the formulas for snap, and then talk a little bit about other actuators like electrostatic actuators, piezoelectric actuators. You can take the call, it's okay. So and talk about piezo actuators and so on. So let's start with electromagnetic actuators. So to make it simple, let's take the simplest form of an actuator. Something like a relay or an electromagnet is built. We have a coil, we have a voltage source. Now, to make it even simpler, we'll say that the armature is pivoting, so we only have one air gap. So we call this air gap X. Because usually sometimes it moves in parallel, and you have two air gaps. But just to make everything simple, we just draw this actuator, there's only one air gap. So if I give the coil a current I, and there are n turns here, what will be the force? So I mentioned already last week that the simplest way to derive the force in any physical question is take the derivative of the energy. The energy can be a function of many parameters, like the current, the number of turns, but it's also going to be a function of x. It does make sense that the energy will be a function of x, because if you change x, the inductance changes, and if you change the inductance, the stored energy changes. And if you make a change in stored energy, there is some work done. So because of that makes sense, the energy will also be a function of x. So we take the derivative of energy to dx, and this will be the force. And this is a standard way of analyzing most electromagnetic actuators. So we have to start, what is the energy? So the energy in a coil, let's see if people remember what they studied. What's the stored energy in an inductor? How much? Very good. 1/2 Li squared, and if it was a capacitor, you recall from last week, it's 1/2 CV squared. Okay, good. Now what is L of an inductor? If we have an inductor with n turns, what is the formula for L? Now that's a bit harder, because that some of you never learned that. Okay, does somebody know what's the formula for L for an inductor? It's actually a definition, it's not a formula. Definition of inductance. Okay, so definition of inductance is N delta phi to delta I, and if it's linear, since most inductors are linear, it is N phi over I. It's only delta phi to delta I if the inductance changes with current. For example, if this saturates. If this saturates, the ratio is not constant, because the phi is changing in a non-linear way with current. But if it's linear, in the linear range, you can just take the total phi divided by total I. Okay, remember, this is a definition, not a formula. Just somebody decided that's how inductance should be defined. The units of it is Henry. Okay, who was Henry? The person who built the first good electromagnet. He did a lot of studies on electromagnetism. I mentioned his name to you before. Okay, now what is phi in a magnetic circuit? And that's something I mentioned several times in class. Okay, this all of you learned. So there is something equivalent to Ohm's law in electrical currents. There is something equivalent in magnetic flux, because the magnetic flux, the analogy is like electrical current or water flux. So there is something equivalent to Ohm's law. Can somebody remember? Ni, very good. Ni over reluctance. And what is reluctance? So everything with magnetics typically is Ni, because we don't care if it's Ni or N terms of I. The total current is Ni. So all the formulas are Ni divided by the reluctance. Reluctance is the equivalent of resistance in a magnetic circuit, and which equals Ni divided by what? What is the formula of reluctance? It's very similar to Ohm's law. So this is, in Ohm's law, this will be V over R. The current is V over R. Here it's Ni of reluctance. Ni. So what is the formula for reluctance of a magnetic circuit?
Length over mu naught times mu times A.
Good, good, very nice. Okay, so the same as Ohm's law. If you have in Ohm's law resistance in Ohm's law equals length divided by resistivity times area. So here it will be the same. It will be length, okay, divide by, in this case, the magnetic resistivity, okay, or conductivity in this case, will be mu 0 mu r times A, where A is a cross section. Okay? Now, if you have multiple magnetic passes, you have a pass in air and a pass in steel, it will be the sum of all resistance. Okay? So now we look at this and we try to simplify things a bit. I mentioned that the mu r of a magnetic circuit is thousands of times higher than air. Okay, so we have the total magnetic flux has to go through two impediments. One is an air gap and one is this. But this path through the steel is much longer, but the resistance of this path is much lower. Because if you look at the formula for reluctance again, which is L over mu 0 mu r A, for the steel L is, let's say, 100 times longer, but the mu r is thousands of times less. So because of that, when we sum the two, so when we do x over mu 0A, which is the air part, plus, let's call this whole path some other number, let's call this L. L is the total path through the steel, plus L over mu 0 mu r A, we can ignore this part. Because mu r is so big, we can ignore this part. So we can simplify this formula that phi is simply Ni divided by L. L is now x, because now we are only taking x into account, the air, x times mu 0A. Okay, so is everybody with me so far? If not, stop me. Okay, good. So now we can plug this into this, and this into this, and we get the energy. So let's do that. So therefore, so we know phi, so we know L. L by definition is N phi over I. So we take phi, divide by I, so I gets cancelled out. So we get mu 0A N over X. Okay? And we plug it into the energy formula is 1/2 Li squared, so it's mu 0A N times 1/2 times I squared. I think I missed an N. It's N squared, because I have N squared, because I have N from here times N from the definition of L, so I have N squared. Okay? So, yeah. So this is the energy times 1 over X, and d energy to dx equals, so all this is a constant basically. This whole thing becomes a constant, 1/2 mu 0 A N squared I squared times the derivative of z. So it's minus 1 over x squared, so it's times 1 over x squared. I'm ignoring the direction of the force. So here we have the formula. All this is a constant, okay, which we'll use later. Let's call it for now capital K. This will be a constant and the times 1 over x squared. So basically, if we take an electromagnet, the force is not going to be linear with current or distance. It's going to be square with the current, nonlinear with current, and inverse square with the distance. But all this just means it's nonlinear. All this doesn't explain snap. Because the fact that actually it's nonlinear is not such a big problem. It's not good. In a servo system, when actuators are not linear, it's not good, but it doesn't mean they can't be used. Now, can somebody intuitively understand why it's not good when an actuator in a servo system is not linear, say with travel? What this means that if x is half, the force will be 4 times, so the force will be non-linear with travel. Now, why is that bad in the servo system actually? Because I'm closing the loop. All what I'm trying to do is control position. So what's so bad if it's non-linear with travel? Now that's need some understanding of servo systems. Pardon?
More calculations.
Okay, but computers today are cheap, they can do the calculations, but there is something fundamentally bad about something which is variable gain. If you think about it, if this is nonlinear with position, the gain of the whole loop changes, because as it gets closer, the gain goes up. So let's make the question a bit easier. What's so bad about variable gain in a servo system? Because if something is nonlinear with position, it's the same as variable gain. And that you should know. What's so bad about something with variable gain?
Lead and lag is a constant.
Pardon? A little bit, but there's something much worse. If you try to build a servo system and one of the components is variable gain, so inexperienced people say, what's wrong with that? The servo will just close the loop anyway and get to the position faster or slower. Okay, but if you understand servo a bit better, you look at it and say that's really bad. If there's variable gain, yes.
Does it spike the error value and then you get like a feedback system?
No. Okay, so I'll tell you the answer. The limit of all servo systems is stability. We harped on it long enough, right? The stability of phase shift, you have too much gain, it oscillates. Okay, if you have variable gain, you have to design your servo system for the highest gain. Like when this comes near closure, the gain becomes infinite actually, right? According, at least by the approximation we have, the gain will become infinite. But let's say it's not infinite, you control the gap, okay? So you only allow the gap to go to here, but the gain becomes very high. Now, if the gain becomes very high, and all the other properties are the same, because the inductance, the phase shift, inductance not, but the other properties, mechanical properties are the same. If the gain becomes very high near closure, you have to design the filters and everything for stability. So you have to design the system that it's stable at the highest gain. Where this armature is almost closed, you have to be very careful with the system, with the phase shift and everything, that it will be still stable at the highest gain. Which means, at a different gain, the system will be sluggish, underperforming. Because of you have to make sure that the highest gain, the phase shift, is less than 180 degrees if the gain is more than 1, right? So basically you have to, the worst case for stability is when it's almost closed, where the gain is highest. You have to make sure there's no phase shift, you have to put some special limitations on the servo, but then at any other position it lacks gain. So when you have a fixed gain servo system, like moving coil actuator, you fine-tune the system that it just is you just reach stability, but you maximize the gain you could. So you look at the peaking, you look at the phase shift, you say, okay, I can add a bit of gain because I still don't have a 180 degree phase shift, so you maximize the operation. But here you have to do this fine-tuning for the highest gain, and at any other position of actuator there will be lower gain, system will work poorly. Is that clear? Good. So that's the problem with systems with variable gain in servo. Now you can say today with computers you can measure x and then change the gain, because the computer can look at x, change the gain of the servo. Basically you take this and you have a variable gain amplifier and you make the whole system behave like constant gain. But there's problems with that too, which I wouldn't get into it right now. Okay, so these systems are nonlinear with control current. That is not, both things are actually bad, because both things mean variable gain. Gain depends on position, and gain depends on the drive current. Because you double the drive current, the force goes up 4 times. Because this is actually F, right? This is a force as a function of x. Okay, so is the derivation completely clear? Because the same type of derivation you use for many types of actuators, especially these nonlinear actuators, where it's not so simple. In a moving coil, derivation was very simple. We said BLI, that's the whole derivation, right? But in a nonlinear actuator, you have to derive the force this way. So let's do a quick other exercise, do the same derivation for a capacitive actuator. So let's say we have a ground plate, a capacitive plate, we connect it to a voltage. This time it's voltage, not current. You have an electric field here and you have an attraction force. The distance is x. Now this derivation is much faster because energy is 1/2 CV squared. We already started this last week. C we already know is epsilon 0 epsilon r a over x times v squared. Okay? In most cases epsilon r is 1 because it's in air. Okay? So we take the derivative of it. So first we rewrite it. We rewrite it 1/2 epsilon 0 epsilon r v squared a. So all these are constants. All these are the big K, the constants, times 1 over x. So the derivative is the same big constants, v squared a times 1 over x squared, and that's the whole derivation. So here it's much simpler. Okay? Now please stop me if you didn't fully follow these two derivations, because we need them later. Good. Good. So now we are getting to the next sig, which is snap. All this is also in your written notes. So if you miss some equation here, not in the video lecture, but in the written notes, you have that. Okay, good. So, by the way, this method of getting the force by the derivation of energy, this is also used in mechanical engineering. And in mechanical engineering, it's sometimes referred to as a virtual work principle, which you may heard or not heard of it. It's a very, very useful principle to derive, say, stresses in a structure or hoop stress in a boiler, things like this. It's a very useful technique in mechanical engineering, this virtual work principle. You can look it up, or if you don't know what it is. Okay, so now let's talk about snap. We have the same actuator as I drew before. To make it simple again, I'll use a single air gap X, coil, okay, and now I'm attaching a spring to it. This is not a coil, this is an actual spring. I'm drawing it because it's confusing, it looks like a coil, but that's an actual spring with a spring constant K. Okay, so let's say that the spring unstretched, reach to here, and we stretch it to here. Okay? So if this whole distance is L, okay, so this whole distance is L, this distance is L minus x, and this is x. Okay, so this thing here, the air gap, is x, the amount the coil can move, and the amount the spring is stretched up to this point is L minus x. The total length of the spring doesn't matter, because in a spring F equals kx, where x is the amount of stretching. So it doesn't matter if the spring is longer or shorter, all that matters is k and how much we stretched it. Good? Okay. So let's say it reaches equilibrium. At a certain current I can hold it at a certain position x. So obviously at this point I can say that the force of this, which we said is the force of the coil, we said is some big K, which I derived just a few minutes ago, times 1 over x squared. And this big K includes I and everything, okay? This has to be equal to Kx. The big K is a constant of the moving iron actuator, little k is just a force constant of a spring, okay? Sim.
L minus x or Kx?
Okay, now you have to watch the signs because right now this is correct. The directional forces are correct because the forces are in opposite directions. Okay, so both were actually minus, but I ignored the two minuses because this force is pulling this way and this force is pulling this way, and the forces are equal. Yes?
The spring force isn't K times L minus x?
Oh, I'm sorry, you're right, correct. Thank you for correcting me. L minus x, of course. Yeah. Okay? Yeah. Okay, and both, if you derive the formula, this was minus and this is minus, but since they are opposing, they are equal, so I ignored the two minuses. Okay? Now, at some point, and we started this last week, at some point this will move, and because this force is going up with a square, and this force is going up linear with distance, at some point it will snap. And we started talking last week, what is exactly the point it will snap? Because even if it doesn't snap, it's still true that this force is square law, one inverse square law, and this is linear. So why doesn't it snap right away? Okay? So basically when it's open, when it's fully open like this, okay, this force is still inverse square law, but it doesn't snap. Okay, but at some point it snaps. So what happened? What's the difference? So somebody answered correctly last week that when this gap is big and you change it by delta x, the increase in force is less than the increase in force of the spring. So if you have a spring and this is L minus x extension and this is x, and this is quite big, although it's inverse square, the change is actually smaller, okay? And you can take numeric examples, okay? Because for the spring, the force increase will always be k delta x. No matter where the spring is, the delta F for the spring will always be k delta x, regardless where it is, okay? For this, the increase will be 1 over x squared minus 1 over x plus delta x squared, okay? So you can bring it to a nicer form, but basically you can see when x is very large, the increase in force will be very small. So not only the force is nonlinear, but the increase in force when you add delta x or remove delta x, actually here x minus delta x, I should draw it with minus because the x goes down. So if x is much larger with delta x, this number can be as small as possible. Imagine if this is like a centimeter and delta x would be a micron, this increase in force will be less than that. But when x approaches 0, this increase in force will approach infinity. Okay? So how would I formalize it? So when I look at this, I say, at some point for a change delta x, this increase in force will be equal to this, and beyond that point, this increase in force will be bigger, so there will be a runaway situation. Because if it came to the point where delta x, moving in delta x, will increase this force more than k delta x, it will keep moving until it snaps. It becomes unstable. Okay? So is that clear intuitively to everybody? So how do I formalize it? It's clear. When I look at it, I say, what does this really mean? It means that df to dx on this side, which is simply k, is going to be smaller than d to dx of this side. So in other words, when the slope of this side, the change of force with delta x, when the slope is bigger than this, you'll get runaway. Because for a change delta x, this force will become bigger, the spring will stretch a bit more, this will become bigger again, and you get runaway. And that's called snap. So let's find out where it happens. So the best way to know where it happens is find out when is delta f with delta x equal for both sides. So what we'll do, we'll take the derivative of both sides. Okay? Okay, so the derivative of this is minus k 1 over x cubed, and that derivative should be equal to the derivative of z, which is minus k. Now we know it's minus k because we know the derivative of a spring is k. It's always k. Okay? Now we can forget the two minuses because they cancel out. Okay? And now we have two equations, and from these equations we can figure out what. Okay, there is two unknowns here. If you look at the equations, we want to find out a ratio. At what ratio between L and X will it snap? So this looks a bit messy. This looks a bit messy because we can't. I mean, we can solve it as a quadratic or third order equation, but there is a shortcut. And the shortcut, when you see equations like that, which look similar, the shortcut is always to divide one by the other. You know that from high school, I hope. Okay? So when you see equations like that and you want to solve it, you just take this, divide by this. So if you divide, okay, when you divide this by this, you get k cancels out and you just get x. So basically what I'm doing, I'm taking this equation and dividing it by the top one. So I divide this by this, divide this by this. So here if I divide this, so the other way, divide this by this, like this. Okay, so I divide this by this, x comes to the top and I just get x. And on this side, if I divide this by this, k cancels out. Sorry, I forgot a factor 2. When I took the derivative, I have a factor 2 here, because x to the minus 2, when I take the derivative, is minus 2x to minus 3. So please add the factor 2. So now, when I divide this by this, I get x over 2. Now when I divide this by this, k cancels out and I get L minus x. So now I reduced it to a first order equation, and it's much simpler to solve. So now I get x equals 2L minus 2x, so 3x equals 2L, x equals 2 over 3L. Okay? So what I find out that when this distance x is 2/3 L, so again I'll draw it here, this is L, when the armature moved until this point is 2/3 L, and it doesn't matter what L is, right? Because the whole thing is just a ratio of x over L. So when this moves until x is 2/3 L, it will snap. And the reason why it will snap, because at that point the forces will be equal and the derivatives will be equal. So again, this line, the bottom line is df to dx, and the top line is f. So at x equals 2/3 L, both the forces will be equal and the derivative will be equal. If I make x any smaller than 2/3 L, the derivative of this will be bigger than the derivative of this, and it will be runaway condition, it will snap. So is this derivation clear? Good. Okay. So bottom line, when I have a moving iron actuator, and if you think for 1 second, this will be true for any 1/x² actuator, because if I did the same analysis for this, I'll get the same results, because this part is a constant, so the rest of the equation is the same as that part. So in this case, the constant is the constant of the moving iron. In this case, the K is the K of moving iron, which was 1/2 I squared mu A and all this. In this case, the constant is the electrostatic actuator constant, but in both cases, F, which is d energy to dx, is a constant times 1/x². So both actuators have actually the same formula, some kind of constant times 1/x². So this derivation is valid not just for moving coil, moving iron, but it's valid for any actuator which has this formula. So any actuator which is called an inverse square actuator, this derivation is valid, because I didn't use here any property of K. Matter of fact, K cancelled out right away. So this derivation is not a function of K. But because of this derivation is valid also for electrostatic actuators. So bottom line is, for any actuator which is inverse square law, you can only use 1/3 of the travel. Because for the first third it seems to work, and once x is 2/3, it snaps. Yes? Oh, thank you. So basically that means these actuators are not very good for servo, because you can only use 1/3 of the potential range. And then they're also not good, because even on this 1/3, the gain of the servo will change. Okay? And we can calculate by how much it will change. It will change by the ratio of 1 compared to 1 over, say, 0.66 squared. Okay, so it changed by about 50%. Even over that third, it will change a lot, the gain. Because this is 2/3, okay, 1 over this, say roughly, is 50%, so the gain will change from 1 to half, or from 1 to 2, even over that 1/3 of the motion. So this explains why non-linear actuators are not used much in servo, although they're cheap and simple and don't need sealing and don't demagnetize. They have every possible advantage, but they have one killer disadvantage, that their gain changes and they snap. Okay, clear? Good. Okay, now let's see if you followed carefully. What happened if I'll have an actuator where F is proportional, let's call it a different K, to 1 over x cubed? Because in theory you can build actuators which are not just inverse square law. You can make an actuator which is inverse cube, inverse force power. So if I have an actuator which is F equals 1 over x², will it snap sooner or later than a moving iron actuator? In other words, will the usable range be more or less than a moving iron actuator? Okay, so what do people think? Pardon? Sooner. It'll be worse. And the reason it'll be worse, because let's take a generic actuator, F equals K1, 1 over x to the power of n. And let's plug in, instead of x², x to the power of n, okay? So the first formula will be k 1 over x to the power of n equals k L minus x. The second formula will be, the derivative will be k n over x to the power of n plus 1 equals k. When we divide them, there is a factor n. Okay, so instead of having just a factor 2, we'll have a factor n. So we'll derive it with a factor n instead of 2. We'll basically get that x is 1 over
n over n plus 1.
yeah, n over n plus 1, exactly. So it'll get worse, because as n goes to infinity, we'll have no active range at all. Okay? It's just the same derivation when you plug in n instead of 2. So basically, square law is already bad. Some actuators have it doesn't have to be an integer. Some actuators can have force equals 1 over x to the power of 1 plus 1.1. So it doesn't have to be 1 or 2 or 3. It could be, an actuator can easily be derived where the force is power of 1.1, 1.2, 1.3. For example, when you design a solenoid, a lot of times you design it not to be square law. So you design it with a special shape inside, something like this. You design it with some shape to try to linearize it a bit. And you do that, you can get any n, which doesn't have to be an integer. Okay? I'll show you in a minute another example of a solenoid where n is 1.5, not 2. So basically, the bigger the n, the less dynamic range you have. But even if n is 1, even if it's 1 over x, n is 1, you will get x equals half. So for n equal 1, which means the force is k 1 over x, you still only have half, because 1 divided by 2 is half. So you still only have half of the range, which is usable. Okay? Okay, another comment. When you take this actuator and you run it from AC instead of DC, and actually a lot of solenoids are run from AC, like solenoid valves in your dishwasher. These are all run by AC. You find out that the operating range seems to be better. Instead of 2/3 L, you find out it's about half L or some number like that. And if you watch carefully last week's demo, when I put the solenoid on DC, it barely moved and then snapped. When I put it on AC, it made a lot of noise, but it seemed to move a lot more before it snapped. So can somebody think, why does it seem to have a better behavior on AC than on DC? Yes?
Is it because the K value has current in it and you're changing the current back and forth?
Okay, but DC, the K value also has current. So why does the current change? So you are in the right direction. Yes?
It's the RMS current, which is 1 over 2 times?
No, because current, that just changes. It's just a constant. It wouldn't change. See, how much dynamic range you have, okay, this depends on the n. Okay? So everything here is k. So somehow it seems that it behaves as if it had a different n. So that means something inside the k is changing. Because we know that the derivation says that it's square law. But if it behaves like as if it was a different thing, it means something inside the k is changing. So when you look at the formula for k, big K, capital K, you look what's in that formula. In the capital K was 1/2 mu 0 a n squared I squared. That was what's inside the capital K. So mu 0 cannot change, a cannot change, n cannot change. So the only thing which can be changing is I. So we come to the conclusion that when we run it on AC, and it seems to have a better range, there must be something here changing which counteracts the inverse square law behavior. And we basically say if x goes down, it must be that I goes down too, so the product doesn't seem to vary so much. Otherwise it will snap at 2/3 of the travel. Okay, so now you have a good hint that I must be in a DC actuator. I is changing, say, slowly. Here I must be changing faster to counteract this. So in other words, when I increase the voltage on the actuator, in a DC actuator, I is changing linearly. I double the voltage, I've doubled the current, because it's simply V over R. But it seems that in an AC actuator, if I take the same circuit, run it on AC, when I increase the voltage, double the voltage, it seems that I doesn't double. Otherwise it'll behave the same as DC. It seems that when I double the voltage, I goes up much less than double. And this counteracts the behavior of 1 over x squared. So can somebody think why? Okay, so what is I in an AC circuit? The formula for I is V divide by.
Is it because it's in the coil and it takes time to catch up?
No. It goes back to what you learned in first year university, okay? In an AC circuit, let's say a simple circuit which just has an AC source and an inductor. Let's ignore the resistance. You just have an inductor L and an AC source, okay? So the current is V over 2 pi FL, okay? But L is changing. Because if you remember just a few minutes ago, we wrote down the formula that L is N delta phi to delta I, and phi is Ni divided by the reluctance. So basically, when the air gap gets smaller, L goes up. Now the reason L goes up is when the gap gets smaller, for the same I, you get a lot more phi. Because L is N delta phi to delta I, but how much phi you get depends on the reluctance. So as the gap closes, the reluctance goes down, L goes up. It does make sense, because think of it, if you had a closed magnetic circuit like a toroid, for the same number of turns, it'll have much more inductance than just a coil without a closed magnetic circuit. Is that clear? Okay, so when you run this thing on AC, as the armature closes, for the same voltage, the current will go down, because the current is this, and L is a function of x. So in DC, I is V over R, but nothing here is a function of x. Okay? In AC, I is V over 2 pi FL, but L is a function of x. So as x becomes smaller, L goes up, and L is actually proportional to 1 over x, because if you plug in the numbers in this formula, just look back in your notes, one page back, R, we said R is Ni times L over mu A. Okay, so this is basically x. Okay, so the reluctance is, this part is the reluctance. Okay, so basically the L is the air gap, is x. So here is x. So now the inductance will go up with like 1 over x, okay, because the sorry, I have to divide by that, it just changes. It's Ni divided by reluctance, and reluctance is x over mu 0a, so mu 0a goes to the top, so I'm getting the same thing you have one page ago, that it's Ni times this divided by x. So in a simplified model, if everything was linear, L over x behaves like 1 over x. So it reduces this equation from square law to 1 over x, because inside the k there is inside the k there is hidden there an I squared, because when we looked what k is, there is an I squared hidden in it. Okay? Now I is a function of x, and x, as I showed you before, L is proportional to 1 over x. Okay? So if everything was linear, if you half x, L will double and the current will half for a given voltage. Okay? So now because we have I squared, you will actually get that I squared is proportional to 1. So I squared is proportional to x squared. To 1 over x squared. Okay? So basically what will happen that these two things will cancel out if the gap was going to be half. Okay, no, it's proportional to x squared, because it's the inverse. It's the inverse. Okay, so basically in a perfect circuit, if the x will half, this part will become 4 times. No, the original was right. Okay, just give me 1 sec. The original was right because for a given voltage, I will go down. So I is proportional to 1 over x squared. The original was right. Because for a given voltage, the force will go up. If x would be halved, that part will become 4 times bigger. But the current will become 4 times smaller. Okay? So the product of I squared by x squared will stay constant. Okay? Is that clear? Because the force you get is a product of 1 over x squared by I squared. Because everything else in K cannot change. Now, if I halve the gap, the force wants to become 4 times bigger. But the I is becoming 4 times smaller because I is V over L, and L is proportional to 1 over x. So I squared will go down as x squared. Is that clear? Okay, so what will be the dynamic range? So in theory, it should be perfect. It should be actually cancel out the square law problem. Because if this exactly cancels out this, I should get constant force, which is great, just like a moving coil. Is that clear, or should I go over that again? Yes?
How can they cancel each other? Because I square is proportional to 1 over x squared. And how can I square cancel 1 over x squared?
Okay, if I... Sorry.
Just from the...
Sorry, I apologize. It is x squared, yeah. Because when x gets smaller, I get smaller. So because if L is 1 over x and I divide by L, then I get x here. Okay, so it is x squared. Okay, apologize. So now when x gets smaller, I get smaller, but this gets bigger. So in a CO, if everything was perfect, in other words, if everything was linear and perfect, I will get that the force is proportional to some number I squared, which is basically I squared times x squared times 1 over x squared. So if everything was perfect, it will be constant force, just like moving coil. So this will be a wonderful actuator because it cannot demagnetize, cannot saturate. It's a very good actuator, but unfortunately this doesn't happen. Now the reason this doesn't happen is this whole model relies on linearity, and we learned before when you have magnetic materials they saturate. So this model that says that we can cancel out the nonlinear behavior by running it from AC, this only works if everything was linear. In other words, it works if we had a very big air gap. If very big air gap, there will be no saturation. Okay, but then we are wasting a lot of the travel of the actuator and a lot of the potential force if there's a big air gap. So the bottom line is you can't win because it saturates. these formulas are all approximations for this part, for the linear range. Okay? To start with, the whole derivation was based on that we said that mu r is much bigger than mu 0, so we ignored all the reluctance of the iron, we just used the reluctance of air. But the moment you approach saturation, as I mentioned before, when it's saturated, mu r equals mu 0. But even before saturation, mu r is not much bigger than mu 0, so we cannot ignore the reluctance of the steel, so this whole derivation is incorrect. Okay? So basically, if you had material which doesn't saturate, this derivation was correct, and if you use the actuator on AC, it would have become a constant force actuator. Okay, so is it clear to everybody why this actuator would have become a constant force actuator if you used it on AC, not on DC? Good. So now the reality is it helps, AC helps, but because of saturation, pretty soon this whole approximation is not true. So that's why when I tried it on AC, you saw a better dynamic range. Okay. Good. So it's not so important that you remember all the derivations, but it's important that you understand the principles. That we derive the forces by taking the derivative of the energy, and you can to some degree counter the x squared behavior by making I change with x. Now, if you have computers, you can force it to linearize by measuring x and changing the I with the computer. But again, for that you have to model the saturation. The software which does that has to know this curve, and this gets very complicated because this curve depends where you're coming from. As you recall, if you came from here or from here, you get different hysteresis loops. So it gets more and more complicated. It's not so simple to write a controller which, given where you are, knows the mu, because it depends how you got to this point. Right? The mu is different if you got to this point like this, or if you got to this point by coming back from here, the slope will be different. So it's actually not simple at all to say, no problem, I'll write some software which takes care of it, because it has many, many factors: temperature, which direction you arrived. So bottom line, if you really want a good servo, you can't use moving iron, except in situations where you have no choice. Because sometimes there are some reasons. For example, you need like infinite overdrive. Moving iron, you can overdrive it to infinity, it will just saturate, nothing bad will happen. Another example where the actuator has to be vented, like open to the air, moving iron will not collect metallic debris or magnetic debris, because as soon as you stop the current, it stops being a magnet, so all the little particles it collected will fall out. So there are some circumstances where you have to use moving iron. But apart from that, don't use it for a servo, because as you can see, it's a problematic actuator to control. Okay. Now, so I also mentioned in the last lecture that a very common actuator today is actually electrostatic, although it can have very small forces. And the reason why the electrostatic actuator became common, because it's very good for MEMS. And the reason why it's very good for MEMS is you don't have to make coils, which is good. And also, when the gap is very small and the actuator is very small, the electrostatic forces are comparable to electromagnetic forces. Yes?
So a quick question.
Yes.
Have they tried using nonlinear springs? Like what is the effect of that?
Pardon?
A nonlinear spring?
Yes, that's a very good idea. Because another solution, excellent suggestion, another solution is take a nonlinear spring which will have the same x squared behavior. It's very easy to make a spring which is k equal x squared. Okay? And if you take a nonlinear spring and you match it with a nonlinear actuator, then you have much, much better range. But it's still not perfect because this is only a model which doesn't take into account saturation. So it still will do funny things, but it will pretty well have a wide range. Now, can somebody think how do you make a nonlinear spring? Like if you take a normal spring, it's a constant k. How do you make a spring where k is not constant but x squared?
Varying thickness?
Pardon?
Varying thickness or diameter?
Okay, varying thickness is difficult. Physically, if you had to make a nonlinear spring, varying thickness is difficult. Pardon?
You could vary the pitch of the helix.
And then what will happen? If you just vary the pitch of the helix, it's still linear. Right? If you change the pitch of the helix, the spring is still linear. There's no effect on k.
Diameter.
No, simpler tricks. There's a few simple tricks to make a nonlinear spring. Yes.
When they touch.
Ah, beautiful. You vary the pitch of the helix, but you make it a compression spring. So these things start touching, and then there is less and less turns, so the k goes up. Is that clear to everybody? Pardon?
Can you
No.
please repeat that?
Yes. If you make a spring, which is a compression, not a tension spring, and you made it like this, that the pitch of the helix changes, and you push it in compression. So every turn shrinks if you have k delta x. So if these turns are close together, as you start applying force, they touch. So cross section looks like this. These are the turns. So when you start applying force, all the turns come this much closer, but these turns are already touching. Now if these turns are touching, you have less free turns. So the k goes up. Because remember, x, total x, okay, is a force divided by k. Okay, so but the total x is divided by little delta x's. Each term gives a little delta x. But if you have less terms, okay, you have less terms, you need a bigger force for self-deflection. So the simplest way to make a nonlinear spring is use a compression spring which is wound with a 1 over x or 1 over x squared spacing. Okay? There's many ways to make a nonlinear spring. It's actually very simple. So that's a very good suggestion. If you had a nonlinear spring, you can increase the range a lot. You still have nonlinearities in the servo because of saturation, but it's much better overall. Good. So there's many other ways to do it, by the way. Once you have a computer, there's many other ways to do it. But without a computer, the two best ways is run it on AC or use a nonlinear spring. But in reality, if you see what people do with these actuators, in reality use them only for on-off, like solenoid valve. Okay, so I talked about electrostatic actuators, and I said that when the things are very small, the force of the electrostatic actuators can be as big as magnetic actuators, and that's why they are very common in micro-machined devices. And I actually mentioned to you that the most popular electrostatic actuator in the world in terms of units made is this thing, which I didn't have to show you. This is this DMD or DLP. This is a chip which has 1 million electrostatic cantilevers used in video projectors. So when you look at it, it just looks like a mirror, but it's actually 1 million mirrors. And this chip has all the electronics to drive them. So under these million mirrors, there is memory, shift registers, interfaces, everything needed to drive them. So it's quite an amazing chip because it has all the processing, and on top of it has 1 million mirrors. Now, because of the snap, okay, I'll let you pass it on. Because of the snap, you cannot use it to modulate the light in a linear way, because this was originally used for TV. And TV is analog, so each one of those mirrors, let's say the chip has 1 million mirrors, and each mirror you wanted to tilt to modulate the reflected light. But because of the snap, they couldn't do it. They actually started with the idea to have it linear. As they, I mean the company TI. TI developed that. So they started with the idea of using it linear, and because of the snap, you could only go a little bit and it would snap. So they ended up doing it that it works by PWM. So they always move the mirrors full. The mirrors are always this way or this way. Typically they move something in the order of 10 degrees. Here it's exaggerated. They only move like 10 degrees because of fatigue of the aluminum. They are made of aluminum. But the way you modulate the light is by PWM. So if you want full light, they're fully on. If you want varying light, you just change the duty cycle. So the mirrors are always full on or full off, but the way you get the variable amount of light is by changing the duty cycle. And that's how these projectors work. Okay? They are basically PWM driven. Yes?
How long do they last?
A long time.
Because aluminum has finite.
Okay, so there's a lot of tricks here. So aluminum usually is a very bad material for fatigue, one of the worst, okay? But if you make it very, very thin and it's the right processing, blah, blah, blah. But the interesting thing is it's not silicon, because the best thing to make these mirrors is silicon. But silicon cannot take a very big stress. Okay, so it actually turns out to be better to make them of aluminum. And if you really want to see how they make them, they look like this actually. They are not a cantilever, because this will fatigue too fast. They are made, each mirror looks like this. And then here they have a strip, and it's a torsion hinge. So this is the opening. Okay, so this is like steady. And this mirror tilts like this. And so the torsion hinges, which are only 1 micron long, torsion hinges are about 1 micron long by half a micron wide, but they only twist 10 degrees and they last forever, which is quite surprising. Okay? So actually, if you look inside this chip, it looks like this. It's squares tilted at 45 degrees sitting on torsion hinges. There's some pictures on the internet you can see close up. So this is called, today it's called DLP, Digital Light Processing. Originally it was called DMD. Okay, and made by TI. It's quite a masterpiece of micro machining. That's the most, I would say that's the most sophisticated micro machine part in the world. Because it has not only the million mirrors, it has all the electronics to drive it. And a million other things all in the same chip. Okay, so now we covered electrostatic actuators, we covered electromagnetic actuators. Now there's a whole bunch of other actuators which are used much less, but you should know a little bit about them. So I would say the next one in popularity is piezo, and we already mentioned it before. Piezo stands for piezoelectric. Okay, so piezoelectric effect is you take a piece of crystal, typically it's crystal material, you put 2 electrodes on it, let's say plus and minus, and when you put a voltage on it, it's voltage driven, not current driven. When you put a voltage on it, that crystal changes dimension. And depending on how you orient the crystal, you can make it change dimensions this way or make it change dimensions this way. In other words, Now this is a bit similar to magnetostriction. I mentioned before that if you take a magnetic material, put a coil on it, it will shrink when you apply a magnetic field. That's the reason power transformers make noise. I mentioned it many times. But magnetostriction is very simple. Whenever you put a magnetic field, it doesn't matter which direction, it always shrinks in the direction of the magnetic field. It doesn't depend on crystal structure. It's a much simpler story. Now piezo is a very complicated story, which unfortunately there's not much time in this course to explain, but I still will explain the principles. Because since this relies on crystal structure, different crystals behave very differently. Okay, so the first piezo material which was discovered is quartz. Quartz is SiO2. If you go to the beach, you get lots of it free, because that's what beach sand is, right? So it's an abundant material. It has a very small piezoelectric coefficient. In other words, if you put 1,000 volt on a block of quartz, say this size, it will move less than a micron. So the coefficient is small, but that's the first material that people discovered the effect. By the way, who discovered piezoelectricity? Who?
The piezo?
No, no. Piezo is just derived from a Latin word, but was discovered by Pierre Curie, the husband of Marie Curie. I mean, I'm sure you heard of Marie Curie, but her husband, Pierre Curie, was also a famous scientist, and he and his brother discovered piezoelectricity 100 years ago, a long time ago. Anyway, so without getting too much into the theory of crystals, you can make a material change dimension a little bit by putting a voltage on it. Typically the voltages are high and the changes are very small. Okay? But it's still useful because, for example, one way to amplify the effect, if you take a beam and you make it from 2 layers, so these are the electrodes, okay? But you make it from 2 layers. This is a material which expands with voltage. So let's say you have one material which expands with voltage. Then you have a second material which shrinks with voltage. It could be the same material, just cut in a different direction, the crystal. Okay? Because now, when you put a voltage on it, the top will expand, the bottom will shrink, and the whole thing will bend. Just like a bimetallic thermostat. Okay? Now here you're amplifying the effect a lot, because if this will be 1 millimeter longer, say let's say that's a centimeter beam, and even the top will be not just a millimeter but a few microns longer, the beam will bend a lot, right? Because it's a huge magnifier. If the beam has 0 thickness, the magnifier is infinity, right? So this is called a bimorph. And that is used a lot when you want to amplify the piezo motion. The most common piezo bimorph in the world is this. Who knows what this is? Pardon? No. No, I'm talking about actuators. Pressure transducers also, it looks the same, but this is an actuator. That is the most common piezo actuator in the world, yes? Almost. These are the beepers which drive you crazy of all electronic stuff. You know, all electronic stuff makes an annoying high-pitched sound when you push the button and do something wrong. So the way the sound is made is by this. It's a disc. The disc has on one side material which expands, on the bottom either nothing or material which shrinks. It's actually enough to have one side only. So you have a metal disc and you cover it with piezo and an electrode. When you put a voltage, this expands, and when it expands, it bends the disc in this shape. So if you go back and forth, at a high frequency, it makes a sound. Typically, it's driven by a few kilohertz, because also it's mechanical resonance. You're trying to drive it at its mechanical resonance, and because these things are stiff, their mechanical resonance is high, so they always make this annoying sound. Especially because they're small. If they're small, their mechanical resonance is high. So pass it very quickly because the lesson is coming to an end. Just have a look at it. You can identify the 2 electrodes in the piezo. Just pass it quickly. So these are piezo actuators. Now, it turns out that piezo have a lot of the problems of hysteresis that magnetic actuators have. So when you draw a graph, of this is voltage, or actually it should be V over M, because what it responds to really is electric field, because it's not the voltage which makes it move, it's the electric field. So V over M is equivalent to Ni. When I showed the hysteresis curve for magnetics, this axis was a B and this was H. In piezo, this axis is V over M, which is electric field, and this is X, how much it moves. So it turns out it goes exactly the same. wires. So basically they're all wired in parallel. And then, when they're wired in parallel, the electric field is very high. Because you have a voltage V, but the voltage V is applied to each layer, so the X is small, or M. This is the distance. So V over M is large because you're applying the same voltage again and again to thin layers. Is that clear? In other words, if this was, let's say, if this whole thing, for example, was L, so the electric field would be V over L, but if I can divide it to 100 layers and apply the full voltage to each layer separately, the electric field will be 100 times more. So if I have n layers, the electric field will be nV over L. Is that clear? It's a bit like adding terms to a coin to change the Ni. So this is the most standard piezo actuator. When you buy a piezo actuator today, especially the big ones, which you can move more, they're all built like this. They are a stack which is wired in parallel. Okay, so this solves the first problem. So now, if you have a stack about 10 centimeters long, you can move 100 micron with a reasonable voltage. Take like a good number of today's stack like this. If you give it 100 volts, you can move maybe 100 micron over 0.1 meter stack. It's like typical performance number. Okay? It's comparable to magnetostriction. If you take a good magnetostrictive material, it's comparable. It's also 100 micron. Another way of saying the maximum movement of all these magnetostrictive actuators, piezo actuators, the maximum movement is about 0.1% of A. And that's it. Okay? Compared, say, to electromagnetic actuator, which can move 50% of energy. So the movements are very small. Okay, so the first problem, the need for very high electric field, is solved by cutting into the layers. So you increase the electric field. Now the second problem, that it has hysteresis, is a bigger problem, and usually it's solved by putting a strain gauge, sticking a strain gauge on the whole stack and closing the loops with a strain gauge. So when you want the stack to move 55 micron, you don't give it 55 volt and say move 55 micron because of hysteresis. You give it a voltage and watch at the strain gauge how much it moved and close the loop to force it to move 55 micron. Okay, so the commercial piezo actuators, the ones which are accurate, have a built-in strain gauge to close the loop. I know I went a bit fast here, but we'll do a quick refresher on Thursday. So, any questions about piezo actuators? Good. Now, there's many other types of actuators, like I mentioned before, hydraulic actuators. Hydraulic actuators are very good because you can make huge forces in small spaces. Because the pump can be somewhere else. So if you have a very confined space, you have to generate tons. The best actuators are hydraulic. That's the reason why in a lot of operations where a person has to go into a tight spot, like the salvage operations, rescue people from a wrecked car, go into a tunnel and rescue people, all the motors are hydraulic. Because in a very, very small package you can put huge power. Yes?
Using that stack actuator with the strain gauge, what's the kind of maximum accuracy? Like, what's your limiter?
Accuracy is pretty good because now it's a servo. The strain gauge measures, so the accuracy should be as good as the strain gauge can measure, but you're still limited to that. That's really the problem. You still get very small motions. And there is other subtleties. Superficially, you would say that should be a very good actuator because I can move it very fast. There's no moving parts, but that's not so. It turns out the materials which have high piezo coefficient, The piezo coefficient is how much it moves per voltmeter, okay? These materials also have an enormously high epsilon r. Like we said, capacitance is epsilon 0, epsilon r, A over D. Now the materials which have the best piezo property have an epsilon r in the order of 100,000. Okay? That means that a stack like this presents a huge capacitance. And you cannot drive it fast, because when you put an AC source here, the current, when you drive a capacitor with AC, again, is V over 1 over 2 pi Fc, so it is 2 pi FVC, and if the capacitance is huge, the current needed to drive it is huge. So on first sight it looks like it's a perfect actuator. You linearize it with a strain gauge, and it's a monoblock, it doesn't have any hinges or moving parts. In practice it's not very useful. It's useful when you make very miniature things, but as a bigger actuator it's pretty useless, because you find right away you cannot drive it fast anyway, because the capacitance here ends up a huge number. But on the other hand, the magnetic actuator you can also not drive very fast, because the inductance ends up a big number, like 2 pi FL. If you drive it at a very high F, you also have a problem. Okay? So both actuators have some limitations at high frequencies, but piezo is very nice and elegant because you can make very controlled small motions. So if you have a scanning tunneling microscope where you want to move the needle nanometers or picometers at a time, piezo is very nice. So for very small motions, piezo is very nice, but when you start building a big actuator from piezo, you realize right away it's no better than a magnetic actuator because of all these problems. Okay, we'll cut it off here. I'll do a quick refresher on piezo Thursday and talk about some other actuators.